Hello class, and welcome to our flipped classroom on heat equations. As always, feel free to pause the video and take notes. So if you were to look at the back of a Regents reference table, you'll see toward the bottom there is a section called heat. And next to that are three different heat equations. And next to those are the definitions of the symbols. So let's start with the first heat equation. Q is equal to mc delta T, where the symbol Q stands for heat or quantity of heat, M stands for mass, and C stands for specific heat capacity. We'll be talking about that a little bit later. Finally, there's also this symbol, triangle T, which is the Greek letter delta. Delta T is change in temperature. And since it's the change in temperature, it really doesn't matter whether the units are Celsius or Kelvin, because a 1 degree change in Celsius is the same as 1 change in Kelvin. So it's just the difference between temperatures. So let's focus on this first heat equation. Q is equal to mc delta T. And let's look at this potential problem. How much heat is required to raise 100 grams of water at 300 Kelvin to a temperature of 350 Kelvin? So right away I can tell this is going to be a math problem. The giveaway is number one, there are a bunch of numbers in it, which usually helps. And number two, it's asking how much heat, literally asking you to find the heat. And we have, as we said earlier, a heat equation. Now let's see if I have enough information to solve this. Well, first of all, we have to establish which one of these unknowns we're trying to find. Since it's asking for how much heat, well, then I'm going to be looking for Q, because remember, Q is the symbol for heat. Now you can put an X in there if you like, but Q is what you're trying to solve for. So Q equals. Next we need the M, and if you remember, M stood for mass. And the mass was 100 grams. The next term is specific heat capacity, C. We need to multiply by that number. But what exactly does specific heat capacity mean? Well, it's the amount of heat required to raise 1 gram of a substance by 1 degree. So depending on the substance you're talking about, it might require a larger specific heat or a smaller specific heat. For example, a piece of metal has a small specific heat capacity. It doesn't take a lot of energy to get 1 gram of, let's say, iron just 1 degree hotter. You could hold it in your hand and the heat from your hand would do it. But water has a much higher specific heat capacity. And it turns out that that's a number that you don't need to memorize, because sure enough, it's in the front of a Regents reference table, right here, under table B, where it has physical constants for water. The one down here, specific heat capacity of water, is 4.18 joules per gram times Kelvin. So let me write that number down. 4.18 joules over grams times Kelvin. Now, depending on which reference table you look at, they sometimes use Celsius instead of Kelvin, because as I said, it doesn't matter. It's the change in temperature. I don't care if it's 1 change in Kelvin, 1 change in Celsius. It's the same change. It's a 1 degree change. And then finally, we need to multiply that by the delta T, the change in temperature. So we're going from 350 to 300 Kelvin. That would be a change of 50 Kelvin. Now, before we actually do the math, I want you to notice something. Grams and grams cancel with these two units, and Kelvin cancel, which means when we multiply these numbers across, the only unit left is going to be joules, which is what we're looking for, because, as I said earlier, we're looking for heat. So let's type this on the calculator and see what we get. We have 100 grams times 4.18 joules per gram Kelvin times 50 gives us a change of 20900 joules. So Q would be 20900 joules. Now, realistically, this number here had only 2 significant figures, so we'd have to round it, but let's ignore that for now. Let's just assume that it had 3 significant figures, and that would be good because those 3 are significant. And remember, we already learned significant figures. So this would be correct. It would be 209 20,900 joules. That would be the answer. Okay? So that's a relatively easy problem to solve for. We were given mass, we were given the two temperatures to find the change, and of course specific heat was given in the reference table. There are many ways this problem could have been structured. We could have done it in reverse. I could have given you the 20,900 joules, given you the change in temperature, given you the specific heat, and asked you to solve for the mass instead. Then the x would be right there. Or there could have been a problem where it was not water that was heated, it was some other substance. And if it was another substance, all that means is it would have a different specific heat, and then of course I would have to tell you what that specific heat was so you could solve the problem. But other than that, it's a very straightforward algebra problem. Now let's look at another type of heat equation. Going back to the back of our reference table, there is another equation here for heat. It says Q is equal to M times HF. Let me get a better view of that. And again, Q is still heat, M is still mass. What does HF mean? Well, it means heat of fusion. And remember, fusion is a fancy word for melting. So let's say I have this equation. The question is, how much heat is required to melt 10 grams of ice at 0 degrees Celsius to water? Notice a couple of things here. Number one, there is no change in temperature. It's at 0 degrees, and at no point do I say I'm changing to a new temperature. Number two, this is a phase change. It's turning ice into water, solid into liquid, which means we're not talking about kinetic energy anymore. We're talking about potential energy. So I cannot possibly use the Q equals mc delta T equation. Fortunately, it said melt, which means fusion. So I know to use this formula. I could have also given a different question where I went from liquid to solid, which is freezing, but it would still be the same formula because fusion and freezing are two sides of the same coin. One is solid to liquid, the other is liquid to solid. It's the same length. So let's see how to solve this problem. Again, what am I looking for? Well, it said how much heat, so again I'm looking for Q. What is the mass? Well, that was given. It was 10 grams. But this time I need something called the heat of fusion. I don't know the heat of fusion of ice. Fortunately, once again, our reference table has that information. Once again, it's the front of the reference table this time. Back where we originally found the specific heat capacity, there's also heat of fusion of water. It is 334 joules per gram. Again, please keep in mind, if this were a substance other than water, I would have to give you this number. So all I have to do is multiply 10 times 334 joules per gram. Watch again as grams cancel, leaving us with what we're looking for, joules, the unit of heat. So therefore, Q is going to be equal to, and I don't think I need a calculator for this, 10 times 334 is 3,340 joules. All right, one last equation we can learn. What if we have water that we want to turn into the gas phase, steam? Well, we have the third and final equation, Q equals M times HV. Notice it's almost identical to Q equals M times HF. Everything's the same except now we're talking about the heat of vaporization. The formula is very, very similar, and the question looks almost the same. How much heat is required to boil, this time, instead of melt, 10 grams of water at 100 degrees Celsius? Notice it's at 100 degrees because we're talking about, hold on, we're talking about water into steam. And again, there's no change in temperature. I never said it went any higher than 100. It's at 100, which means, once again, this is not a kinetic energy problem. This is a potential energy problem. We are just changing phase. So, I'm looking for heat. Heat's Q. Mass was once again given, 10 grams. But what is the heat of vaporization of water? Well, no surprise. The reference table just gives you this information. Back on the same table we found the other two numbers in the front. Physical constants for water, heat of vaporization of water is 2260 joules per gram. And again, yes, if this were a substance other than water, we would have to be given that information. So the grams cancel with grams, and Q is equal to 22600 joules, 22,600 joules. Now, if I wanted to make this problem more challenging, I could have used more difficult numbers. I could have used a substance other than water, in which case I'd have to give you a different heat of vaporization. Or I could have gone in reverse. I could have given you the heat that was absorbed by this process, given you the mass, and have you solve for the heat of vaporization. But all in all, it's just a very straightforward algebra problem with only 3 or 4 variables, depending on which formula you're using, and you have to solve for one of them. The units all cancel, leaving you with exactly what you're looking for. So just to review one more time, the 3 different equations that involve heat are Q equals mc delta T. You only use this one when there is a delta T, a change in temperature. So if there are not 2 temperatures listed, obviously it's not that formula. You're not doing a kinetic energy problem. If you are melting, or the opposite, freezing a substance, use Q equals mHF. And if you're boiling, or if you're condensing a substance, because condensing is going from gas to liquid, which is the exact opposite of liquid to gas, use Q equals mHV. Where do you find numbers like specific heat capacity, which is C, or heat of fusion, HF, or heat of vaporization, HV? These numbers, if we're talking about water, are in the front of your reference table. They are right here. Heat of fusion, heat of vaporization, specific heat capacity. Again, these are all for water, but what if it's not water? Well, then I would have to give you that information, and then you just plug it in and solve. And that is our lesson on heat equations.